In this recording, we are going to introduce or we're going to interpret what the columns of this WH means. We told you that in the discrete Fourier transform synthesis, these DFT coefficients are scaling by each of these columns. So it is important for you all to understand what each of these columns represents and why it can reconstruct the signal vector X. Now, we remember that Wn to the power of minus Kn is defined to be this equation. Let us fix one of the k's first. We're going to use k equals to 1. And we are going to vary n for capital N equals to 8. So a vector of 8 dimension. So what is this element then? It is 2 pi divided by 8 times k equals to 1, varying n equals to 0 to 7. 2 pi divided by 8 is pi over 4 is equals to 0.25 pi. Since we are multiplying by 1, it's always 1, and n is varying. So we are varying n here, so n goes from 0, 1 until n equals to 7. And so this is the vector. And what does this vector looks like to you? It is basically a vector, a complex exponential that is going to rotate as n is increased. So how is it rotating? So let's plot. So this first row here is plotting for this vector. And in the 2 dimension, you can see where are the points landing. And if you count, there are 8 points. But actually in the 3-dimensional plot, we can exactly see how is it rotating. And it is a magnitude 1 vector, a complex exponential rotating anti-clockwise direction as n goes from 0 to 7. So let's count the point. This is x0, x1, x2, x3, x4, x5, x6, x7. And then x8 will go back to the same point here. Right. So you can see this in 3 dimension. It is very nice. And of course in 2 dimension, it is just sitting on the complex plane. Over here, we are plotting the real versus the imaginary across time. So the take home, the first column now we understand. The first column vector of the W matrix here, the first column represents a complex exponential rotating one complete cycle using n sample. Now what about the second guy? So let's see. We substitute k equals to 2 now. K equals to 2, and we substitute into W8 minus k. K is 2, and later n. And of course, we put it into the equation. 2 pi over 8 times 2 times n equals to 0 to 7. So, you work this out. 2 times 2 pi divided by 8 times 2 is of course 0.5 pi. So n is varying, so we fix the 0.5 pi, and then we are changing n here. And now you also think, hey, isn't this also another complex exponential vector with magnitude 1? And the rotation is also rotating, and it should be rotating also anti-clockwise, but it is different to the first one because actually it's rotating faster. At each step, it is moving by 0.5 pi. So let's see. This figure shows that this is the first point, and this is the second point, and at each step, he is rotating by pi over 2, 0.5 pi. So this is the figure of the second column of the IDFT matrix. This vector here shows that in n step, he actually moved 2 rounds. Okay, so that's what we are saying, that this is a second harmonic, because if this is the first harmonic, it used n step to move 1 round. Here it is twice faster, we say the second harmonic. And then if you now understand this concept, then when we use k equals to 3 here, this is moving even faster. It's moving the third harmonic. So let's go back. So I've shown you k equals to 1, the first column, k equals to 2, the second column, and then of course you can go up to k equals to 7, the last column. And as you're moving faster and faster. What about k equals to 0? Why is it all 1? Well, if you actually substitute into this equation over here, and when you set k equals to 0, so it's 0 multiplied by n, so of course this is 0, and any value of n doesn't matter because it will end up with 0, and therefore ej0 is 1. So it doesn't matter what n is, you'll get 1, and hence the first column is all 1. So remember, I will always use index from 0. So this is the 0th column, first column, second column, until n minus 1 column. And now we can interpret the WH matrix. The WH matrix consists of complex exponential rotating at different harmonics. This is the 0 harmonic, first harmonic, second harmonic, up to the n minus 1 harmonic. The 0 harmonic is all 1s because when k equals to 0, when we substitute in the equation, all these entries will become 1. K equals to 1 is the most interesting one because when k equals to 1, it takes n sample to complete 1 cycle. Okay, k equals to 2 takes n sample to complete 2 cycle, and so on and so forth. Okay, so with that understanding, we now can appreciate the WH matrix. Thank you.